In this video, we're going to look at the inverting amplifier configuration based on an ideal op-amp. So you can see we have our ideal op-amp in the middle of our circuit here. We have the non-inverting input to that op-amp connected directly to ground, and we have the output of the op-amp connected to the inverting input via a feedback resistor R2. So we can say that this op-amp is in negative feedback. We also have an input resistor R1. You can see that our input voltage comes in on the left hand side here, VI, and our output voltage is on the right hand side there at the output of the op-amp. So we know for an ideal op-amp with no external circuitry, the open loop gain A is equal to infinity. So what we want to work out here is how the current configuration with the feedback resistor and the input resistor affect our gain and our transfer function. So that being the relationship between V out and V in. And our gain, of course, will be equal to V out divided by V in. So we can work this out from our circuit by simply applying some of the basic laws of electronics along with the characteristics of our ideal op-amp. And in this video we'll talk through those in a simple step-by-step basis. So step one is to very simply recognize that our non-inverting op-amp input, which we'll call V2, is equal to 0 volts. That's straightforward as it's connected directly to ground. Step 2 is a little bit more complicated. So here we're going to show that V1, that is our inverting input, is also equal to 0 volts. Now the reason for this is that we have a virtual ground set up by our ideal op-amp. The virtual ground being the op-amp characteristic where it forces the two input voltages to match each other, and as V2 is connected to ground, that matching must equal to 0 volts. So this can be a little bit of a difficult concept to get your head around, but it can be shown mathematically. If we just consider the case of the op-amp by itself, which we've looked at previously, we know that the op-amp's output V out is equal to the open loop gain A times the difference in input voltages V2 minus V1. Now if we rearrange that, we can see that V out divided by A is equal to V2 minus V1. Now we know mathematically that if A is infinity, then the left hand side of this equation must equal 0. So we therefore have V2 minus V1 equals 0. And that can only be true if V2 equals V1. And we already know and have shown that V2 equals 0 volts. So V1 must therefore also equal 0 volts. So that's the concept of this virtual short circuit between these two input terminals, and how the op-amp's ideal characteristic forces the voltages to match each other, in this case causing a virtual ground of V1 equals 0 volts. For the next step, step 3, we simply work out the input current I in, or I1 here. So this is the current going into the circuit through R1. So we can calculate this by simply applying Ohm's law. We know that the I1 current must be the voltage dropped across the resistor R1, which would be V in minus V1, which we know is 0 volts, so minus 0 divided by that resistor R1. So therefore we can say that I1 is equal to Vn over R1. Step 4, we simply recognize that as our ideal op-amp has infinite input impedance, there can be no current going into the input terminals. So this, let's call it I minus current, must equal 0. And that's due to the infinite input impedance characteristic of the ideal op-amp. So step 5 follows directly from that and states that our I2, the current going through resistor R2, must therefore equal I1, because none of the current is branched off into the inverting op-amp input terminal at V1. And we already know that I1 equals Vin over R1. So that brings us to the final step of this circuit analysis, and that is to work out V out. So we know that our output voltage is going to be the voltage at the V1 point on the left of R2 minus the drop across, the voltage drop across the resistor R2. So minus I2 R2. So substituting in the values that we already know for this, we know that V1 is equal to 0 volts, so that's 0 minus. We know that I2 is equal to I1, which equals Vin over R1. So Vin over R1 times R2. And now we can say V out equals minus Vin over R1 times R2. So now we have the transfer function of our circuit. And of course from here it's very simple to get the gain being V out over Vin, which in this case equals minus R2 divided by R1. So you can see from this relationship and this gain equation that the actual amplification, the gain of your op-amp, can be very easily controlled by simply choosing your resistor values for R2 and R1 to get whatever gain level it is that you're looking for. So we now have a very controllable amplifier by the simple addition of two basic components.